Welcome to Chapter 9, the Part 4 screencast for gases. Have any of you seen the movie Dances with Wolves? If you haven't, I recommend you watch it. It's a pretty good movie. And if you have, you might remember the opening scene in which Kevin Costner plays a Civil War officer who was wounded and goes into battle and is rather heroic. And then quite a few other things happen in the movie that don't have much to do with that. But the reason this is being brought up is that during Civil War days, and certainly before then, surgery and dealing with wounds and injuries was pretty brutal. And one of the reasons was that anesthetics were not very common. And in fact, often the anesthetic of choice was drink a bottle of whiskey and get crazy drunk, or chew on a strap of leather and just deal with the pain. Well, anesthetics have been used since 1842, before the Civil War. Diethyl ether was used as an anesthetic, but it had some pretty nasty side effects, made you pretty sick afterwards. And when surgery started entering the electronic age and there was electrical equipment inside the surgery suite, ether's very flammable, and it could catch on fire if there was a spark or a little bit of electric discharge. So for a number of reasons, since about the mid-1900s, different anesthetics with less bad side effects and less flammable characteristics have been used, and a common anesthetic is a mixture of what's called halothane and oxygen. So here's a little picture of some Civil War brutality, and fortunately we don't have to endure that anymore. So let's suppose, now dealing with gases, that we have a 750 milliliter flask at 25 degrees Celsius, and it contains 0.285 moles of halothane and 0.13 moles of oxygen. Both of these are gases. So here is meant to be a representation of the halothane, which is the orange, and the oxygen, which is represented by the green here. And we have a little more than twice as much halothane as we do of oxygen on the basis of moles, and both gases are in this container or flask. Now, the volume of the flask is occupied. Both gases take up 750 milliliters, so the volume's the same for both, as is the temperature. They're both at 25 degrees Celsius. But halothane and oxygen have different numbers of moles. So how do we deal with a gas mixture like this? Well, the first question is to determine the partial pressure of the halothane, and since the volume the halothane occupies is 750 milliliters, the temperature it's at is 25 degrees Celsius, and the number of moles of halothane is 0.285 moles, the oxygen we can just ignore for purposes of determining what's called the partial pressure of the halothane, because it is simply the pressure due to only the halothane moles. So this is actually just an ideal gas law constant. PV equals nRT. We can solve for P equals nRT over V. And for the halothane, the volume, temperature, and number of moles are known. We plug that into PV equals nRT, solved for P. Cancel units in the usual manner. Do note you better go to Kelvin for your units. And what we find is the pressure of halothane in this particular instance is 9.3 atmospheres. So this is the partial pressure due to just the halothane in this container. All right, second question, determine the partial pressure of oxygen. Well, just like before, the oxygen occupies the same volume as the halothane did. It's at the same temperature, but the number of moles of halothane are different, and the equation we use, PV equals nRT, is the same, but the T and the V, and of course R, will be the same numbers, but the number of moles for oxygen is different in this case than the number of moles of halothane. So we calculate in the same manner, but we are careful to use the oxygen values, not halothane. Cancel units as before, and we get the pressure due to just the oxygen, which is called the partial pressure of oxygen, as 4.24 atmospheres. And note that the pressure due to the oxygen is a little less than half of the pressure due to the halothane, and that's because the number of moles of the oxygen is a little less than half the number of moles of the halothane. Now, the total pressure of this mixture is going to be as simple as the pressure of halothane is 9.30 atmospheres, the pressure of oxygen is 4.24 atmospheres, and the sum total of both of those is 13.54 atmospheres. And therefore, this is a easily generalized example. The pressure of several gases mixed together, well, if you add up the partial pressures of each of the individual gases, you get the total pressure of the mixture of gases. So one other thing to note with this is if we're dealing with things on a molar basis, which is what we should do because moles are proportional to the number of particles, note that we have 0.285 moles of halothane, we have 0.130 moles of oxygen, which gives us a total of 0.415 moles of gas particles. And we're not here distinguishing whether they're halothane or oxygen. We just have this total number of moles of particles. Well, what this means is the number of moles of halothane divided by the number of moles of total particles. This is what's called the mole fraction. It's the fraction of the total moles that is due to just one of the gases, in this case halothane. And it's simply a number. In this case, it's 0.687. And what this means, of course, is that we have 68.7% of the molecules of gas are halothane molecules. Now, just as similarly, we can do the calculation to determine the number of moles of oxygen, but since the total container, or total gases in the container are just the halothane and the oxygen, if it's 68.7% halothane, then it's got to be the remainder, 31.3%, due to oxygen. So we can calculate this. The mole fraction of oxygen is going to be the moles of oxygen, 0.130 moles of oxygen, over the total, 0.415 moles. And when we do the calculation on that, we get 0.313, which of course means 31.3% oxygen, which we already knew. So this is a general result. It's called Dalton's Law of Partial Pressures. The total pressure of a gas mixture is equal to the pressure of all of the gases added up. So pressure of gas 1 plus partial pressure of gas 2 plus partial pressure of gas 3 if there's a third gas, etc. And then the pressure of each individual gas is equal to the mole fraction times the total pressure of the gas. And the mole fraction is the moles of that gas divided by the total number of moles of gas particles. So, one more example of this. Example 13, if we're in Mexico City, where atmospheric pressure is 0.755 atmospheres, it's at about 7,000 feet, so the atmospheric pressure is quite a bit less than at sea level. What's the partial pressure due to just oxygen, and what's the partial pressure due to just nitrogen? And to solve this problem, we need to be aware that air is about 78% nitrogen and 21% oxygen in terms of moles, number of particles. And then it's also about 1% argon and very small percents of a bunch of other things as well. And to calculate the partial pressure of oxygen, we just simply take the percent that of the total air that is oxygen, but do it on a fractional basis. So 21% is 21 over 100, or 0.21. Multiply that by the total pressure, and it's 0.16 atmospheres. And the pressure due to nitrogen is the mole fraction of nitrogen, 78 over 100, which is 0.78, times 0.755 atmospheres, and that works out to be 0.59 atmospheres. And then note that 0.16 and 0.59 do add up to 0.755, and not quite exactly the same because of slight differences in our significant figures. We have our answers here to 2 sig figs, but we started with 3 for the total pressure, so we're going to not quite exactly add up because of those round-off issues. All right, let's stop that one here, and let's go on to another screencast on a new topic next.